I'm actually going to go ahead and get started because we have a set number of things that we need to do today, because this is our last non-homework day. Before that, I gave you the stapled article. You can tell there's no equations on that. That is purely for your own reading, but I found it very interesting. There's actually a physical chemist who works in computational physical chemistry. In fact, there's a physical chemist who's well known for being a Christian, and also he tries to run his lab. He's kind of like the Francis Collins of physical chemistry. And I don't know if I think people are saying that he should win the Nobel Prize, but there's a bit of a bias against computational chemistry, which is what he does. This is his friend, who's another accomplished physical chemist and also a Christian. And he tells stories about Newton, Einstein, Heisenberg, the papers that you've been reading, and then he tells a story about Jesus as the last one. I think this is really interesting because it's about the weird quantum world that we live in. And so this is not going to be on the test. And you might want to save it for summer, but I do recommend that you read it to think about just how weird. It will help you think about the weirdness of the quantum world and the fact that the uncertainty principle, the one thing that we don't talk about that much in this class, but the uncertainty principle is related to the fact that light is quantized, everything is quantized, but that also means everything is uncertain. So all that is to say, it's more about physics and chemistry, but that's a lot of our stuff that we talk about. All right, so what I really want to do is I want to ask you to buckle up, because this is a class. Look at the homework sheet that we're starting. Our goal is to finish this homework sheet, and also all of the chapter 20 problems from modern thermodynamics are actually covered today. So today is where we tie everything together and we tell you how to solve problems. There's a few cases where they give you justifications for why are we doing things this way, how can we be justified in doing that. You know what I'm going to do? I'm going to say let's be practical, let's trust them even more than usual. You can go into the book for justifications, but I want to work back from the problems. We have these problems in front of us. We want to know how to calculate the partition functions. And I said that you can, once you calculate the partition function, you can calculate all these other things. And I actually want to give you the tools to be able to do these calculations. The other thing is that we're going to have examples. We're going to have solving problems all the way through it. Some of the problems, so you have answers for most of the problems. You don't have answers for 2 of the modern thermodynamics problems. And you also don't have answers for the Dill problems. But for Dill problems, I'm going to show you his examples from his book, which should lead into very naturally. And I'm going to give you some hints. So all we're going to do is we're going to be very problem-focused today. I might even refer to some of these things. Yeah, we'll see. But just notice that we're tying it all together, and we're going to give you lots of examples. I have printed out a PDF of these slides because I want you to be able to look at these slides like you did an answer key. And so let's jump into it, and we'll kind of move back and forth. The way you take notes on this should be informed by the fact you want to take notes on which part of this complex thing is most important to solving the problem. For example, one of the equations that you will use, you're going to use this, which is actually pretty straightforward, but you just have to figure out what Q is. Remember that Dill started to talk about what Q is, and you're going to have his exact examples. We're going to do it instead of being for just abstract energy levels, we're going to say what exactly are the energy levels for rotation, translation, and vibration. And so we're going to have very simple examples, but they're literally going to be calculating this stuff from the bottom up. So we can calculate U, S, F. We're going to have one side at the end about calculating mu, but remember that mu, chemical potential, is related to K. So if you look really quickly at this, just notice that the back of this, I've actually reproduced a page from Dill. And this is about predicting K, predicting what the equilibrium constant is going to be. When you see that, you should be thinking immediately, this is something along the lines of mu, or you know what K is. You know, he actually starts with K, and he calculates the partition functions for each of the 3 molecules that are involved. This is where we're going to end up, and that's why I've given it to you. This is also on the slides. Once we get to this, we will be ready to take this homework. But we're going to start off by talking about, we talked about probabilities. Now we need to get it to terms that we'll actually use that are energies and entropy. So let's jump in. We're gonna, and by the way, some of this stuff, you might have gaps. If you have gaps about why, I suggest going to the book for that section, because he describes it, actually he describes it one way and Dill describes it another way. Between the two of them, I think you can get a full picture of what's going on. And you really only get a picture of what's going on by doing it, by using the math. That's why you have to have more calculus to be able to do this. I'm not going to bother the 3410 people with this, because this is where you use your math reasoning ability. Okay, so let's reason. The Boltzmann probability distribution, we talked about, you can get probabilities, you can have energies, E, and G is the degeneracy. It means you have multiple configurations that have the exact same energy. So in other words, there's multiple ways for the system to be that exact energy level. And what we care about is how much is at what number of energy level. So degeneracy is actually a nice time saver for us. It can actually help us calculate pretty easily. And let me just say something. The G is actually a concept that's on the ACS. We'll talk about the ACS. In fact, I'm going to focus on the ACS on our math day. And by the way, just to let you know, in case you forget, we have the awards ceremony is going to start. We're going to miss the first part of it, but they're not going to be into the part that you all need to be at that. We'll just have to show up late because we need to get through that. I think you need the math day. So I think we need to talk about these things. So at 5 o'clock, I'm going to try to just cut myself off, and we'll all walk over to the place, and we will go do awards, and people will get awards and cake for everyone. So, okay. So all that is to say, we've talked about these things before, and this is the energy level is proportional to the number of particles in that state. This is the fundamental concept. But it's proportional through an e to the minus x function. It's also proportional to the temperature. And so we're really interested in how many particles are in what state. Everything we're doing boils down to this. That's what's statistical about statistical mechanics, which I'm not used to saying. So we call this the occupation number of the state, like what fraction of molecules are in that energy state. And the relative number of particles, if you calculate this out, you actually get this equation, which we've had before. The only difference is here you have the degeneracy. So you can have like 2 energy levels up here, 3 energy levels down here. They're at the exact same number, but there are different places for the system to be. Just because it's the same number doesn't mean it's the same number for energy can apply to multiple states. All that matters is how many states at what energy. So you see that shows up. And so, like, yeah, well, probably, I know there are some ACS practice test problems that will go for exactly this concept. So you just multiply it by 2. If there are 2 states, you put a 2 in front. If there are 3 states, you put a 3 in front. Okay. So we're going to use this notation, the average value, because we have a population, they have a distribution. The average is the first thing you want to ask. What's the average speed? For example, the speed of sound problem is an average speed problem right there. So the average energy of a single particle is sum up of all the number of particles with an energy by that energy, and then you divide it by the total number of particles. This is very similar to our partition function. Remember the partition function, we're doing this for energy levels. And so just notice that we are using averages what's statistical here is that we're using averages for all these things. Okay. So in general, we have this is, you probably can do this without seeing the formula. I actually want you to see though, how the formula, this is the formula for taking an average. You add up all the things and you divide it by the total. Okay? And if you have 10 molecules with 100 kilojoules energy, you multiply it by the energy and you're getting the average energy of that thing. Okay, so the average value, this is the same thing. Okay, so the other thing is that if you have a function, this is the way to do it for a function. Look how it looks the same. It's just a function for x instead of a value for x. The function just adds up. Okay. So that's taking something that everyone knows how to do and making it kind of mysterious, but we're going to put it in this terms. This is something you might not know how to do. So if we take the average value of e squared, it's going to be, according to this formula. This is the way that we represent this. The standard deviation in E is defined as the delta E squared equals the difference between each E and the average squared. Again, you square it so you don't have to worry about the negatives versus positives adding up wrong, okay? You just care about the deviations, so you make them all positive by squaring them. And if you take this, you can actually see one of the reasons why it's so easy to calculate standard deviation is it's actually E squared average minus E average squared. Okay? You actually probably get this in statistics rather than calculus. But basically, that's what we want to do. And we want to use calculations like that. That's a key math trick. So, for example, remember what we're doing here. We have energy levels all the way up, and the particles are going to be distributed in an e to the x function. Just realize that the e to the x function can be steeper, and it can be vertical, but it can't be like negative. E to the minus x is never going to go like this. At most, it's going to go like this. So you have all the same particle, you get the same number of particles in every single state. Usually, you're going to have more in the lower states, and the question is how much more. If you want to know the total energy, add up all the ones multiplied by the energies for each one, and then divide it by the total. So this is just saying the same thing in probabilities, and we have this equation that entropy is related to the probabilities through this natural log. By the way, the reason the natural log is there is part of is related to the fact that the e to the minus x is the fundamental way particles distribute themselves. But this is actually, so this is the first homework problem from modern thermodynamics. It tells you to use this to find this, and we do have a homework solution for it. So if we're talking about W, we're talking about natural log W is what we get S from. Remember Boltzmann's tombstone. And W is a factorial, the factorial of the one thing you're looking at, divided by the total number of factorials that you have. And so the entropy is Boltzmann constant times the natural log of this microstates quantity. So we're dealing with like a mole of molecules. N of K is going to be around 10 to the 20. Okay? We have a lot of things to calculate. So we don't want to calculate this directly, but the cool thing is a factorial for a 10 to the 20th would take us all year to calculate. But the cool thing about math, there's an easier way to do it. Stirling's approximation says the natural log of a factorial is approximately equal to a natural log of a minus a. If you take this, you can actually take this to get from this to this. And it turns out that this contains a factorial. Just realize that this contains this. That's why you're using this on this side, and then you're bringing it out to this. I'm going to let you work that out for yourself, but also follow the exact key that's given to you. So once you do the log math, you basically can say the number of molecules in each level over the total is related to the natural log of W, and then you just multiply by kV to get the entropy. Very powerful, actually. And this is what we're using all the way throughout today. The important thing is that it's average natural log average, or probability natural log probability. To get, so we're going to have to be done with probabilities, and the one rule about probabilities, they're always between 0 and 1. That's the cool thing. In the same way that this, if you look at this definition is also always between 0 and 1. Number of molecules in a certain state over total number of molecules. So this is where the fun begins. We've actually had this before. Now we're going to use it. So remember that probabilities, to make the probability, relate the probability to the energies, the probability of being in a certain energy is equal to the value of that energy divided by kBt. By the way, 1 over kBt is going to be beta, and you're going to see that all day today. In fact, I suggest, I'm going to write it over here. Hopefully I write it correctly. I'm going to write it over here. I think that as long as Nixie can see this. Believe me, you'll thank me for this. Right here, they're spelling it out, but later they're going to have beta. For every energy level, we have an e to the minus x function. And the reason why we have 1 over q is the 1 over q is our total term. It's our total description of all the energy levels that are accessible. Remember, energy levels can have different spacings relative to the temperature. And that's everything that's going on here. So they call this the canonical partition function because it's basically it's the sum of all the energies and all the energy levels that you can have for a system. And so you have this. You've probably written this before. So, you know, you can go back to your notes for this. And we will have this again. Now, there's one thing that they do. This is something I'm going to gloss over. Basically, there's an issue with applying this to different ensembles. And what you do is you actually take a big view where instead of looking at particles at energy levels, you talk about the whole system of particles at energy level, and you set it to constant temperature. Because we're calculating everything relative to temperature, we're fixing that. If you do these tricks, then you can do these calculations, but this doesn't bother me. The extending this from a single particle to a group of particles, and realize it's the same idea. It's just that these groups of particles by themselves do not follow the e to the minus x distribution. You see how we have fewer ones at lower temperatures. That's because we're not talking about particles individually. We're talking about collections of particles. And if that doesn't make sense to you, make up your mind to trust them and go back to the book if you want to argue with them. I've read it and I like it. Okay, here's our fundamental beta, 1 over kBt. So we can write q like this, and we'll be saving ourselves some pen strokes. This might be your hint that you're going to be writing this a lot. Because you have an e to the minus x for every state, every molecule that you have. So the total energy is going to be the sum of all the energy levels, overall the levels. And you have the probabilities, and just to remind you, the sum of all the probabilities must equal 1. Then the entropy to the system, here we're just applying the different terms that we have up here. This is similar to what you already did. We have this, but now we're going to plug this into here. We're going to be talking about the probability of a U, this specific form of energy, total internal energy. So we plug this in and we get this, okay? Now what we do is you actually, so now the question is, how can we solve this into a simpler form? It becomes simpler. If we just do a few things, if we follow natural log math, actually getting from here to here requires some natural log math type of things, but you end up with minus natural log of q because it's the denominator. It's technically q to the minus 1, you're moving the minus 1 down. Anyways, this is the kind of thing that we actually do most in this class. So you've simplified the e to the minus x function by having the natural log calculate out that leaves behind the natural log of q. Then we take this and we multiply it through. So we end up with this, and we have the natural log Q still down here. We have summations of probabilities here and there. What's really cool about this is KB times beta. That cancels out. That leaves a T. This is actually the sum up of this is going to be U. So we end up with U over T plus KB. This is the energy of the whole system, which is what we've been calculating all through this class. Now we've got to it from probabilities instead of from physical measurements. Plus KB natural log of Q. This is another form of this equation, but it's done for energy. And we've gotten to energies, we've related S and U to Q. This is something you can do something with. And always think your first question with these is, what is Q? That's why we took so much time in the last lecture with talking about defining Q. And that's why I think Dill does really well. Once we get U and S, then we can get free energy F. It's actually easier. You can actually, free energy F is defined, this is the, I forget, this is the Helmholtz energy? That's what we call it. It's equal to U minus TS. Remember that? That's why I like having this last, because we actually go back to these previous things. Helps you review for the test. And by the way, the test is only on the second half of class, but I can't say that we won't bring stuff back, because here it is. So that means that this, you can take this and rearrange it, and you end up finding that F is KBT natural log Q. If you have Q as a function of these normal parameters, then you can say that U is actually equal to the derivative of natural log of Q over beta. This is another thing, I'm not connecting all the dots here, but the dots to be connected are dF over dt. Yeah, that's actually the dot, oh, it's right here. Well, U equals dF over dt, and then chemical potential mu can also be done by taking this and doing dF dN, and you can do pressure by negative dF dV. Mostly, however, I believe most of your homework is U and S, and the ones with K involve chemical potential. But those actually work themselves out differently. This is what's the kind of thread that will show up on the ACS test. By the way, I do want to make sure that, like, as you're working through it, I want to make sure that you can go back to a particular part of this lecture and pull up the slide and really go through the homework problem. Okay, so remember that we had the two-state system. This is back to Dill. The two-state system that we showed you was called the Schottky two-state model. And it's that simple model where we have, 4 things at the higher level and 1 thing at the lower level. And we talk about how the energy changes. And we got something like this. As the temperature increases, the average energy goes up. Remember, you can have at most both levels equally populated. You can never have the second level higher than the first. The higher level higher than the first, because the only thing you're doing is changing the temperature. There will always be, at most, an e to the negative x, which means at most a vertical line. So it's going to, we had this last time between 2 energy levels at 0 and at E0. And remember that we had this. This was a single particle partition function for it. The probability of being at level 1 is 1 over Q. The probability of being at level 2 is, and by the way, Q is just the total number of energies we can have. Basically, we have an energy level 1 and energy level 2. And the Q is the total energy levels added together. So you see energy level 1, energy level 2, added together is on the bottom. So you find the average energy by taking the derivative of the QdV. Actually, the slope of this line will actually give you the average energy if you also then divide it by the partition function, okay? All that is to say, here's Q, there's Q. dQ, you end up taking the derivative of Q, and you end up getting this. This is in the beta form. and this is just what the KT spelled out. So these are actually the same equation over and over again. But the average energy in the molecules, according to the temperature, as you raise the temperature, the average energy raises. But it saturates as E over 2. If you look at this, what's the maximum that this can do? If you go to infinity, if temperature goes to infinity, this goes to 1. This goes to 1. So you have EO over 1 plus 1. EO over 2. And that's what it means as temperature goes to infinity. As temperature goes to 0, what happens? Temperature goes to 0, that also goes to 0. Am I right in that? If I remember that right? E to the 0 is actually, as temperature goes to 0, it's over 0. So that's the hard thing about temperature being in the denominator. It's actually E to the negative 1 over x. But all that is to say, as temperature goes to 0, the number of energy. Actually, I'm doing the average energy, but as temperature goes to 0, average energy should go to 0 as well. I believe that's true. If it's not true, you have it recorded so you can throw it back at me. Okay. So that's the thing. You can find from this model, once you have Q, you can find all these things. Average energy is what was on this slide. This is how you calculate it from Q. dq over d beta divided by Q, negative. We go back to our previous relationships. And again, this is the heat capacity relationship. Not complicated. It's how the energy changes with temperature. So you have an expression for this. We got this on the last slide. So we have that over dt. We actually have, we can put it in terms of beta by introducing beta here by d beta dt, and then you can actually d beta dt disappear, or it actually ends up giving you this n over kt. So basically you can have the dE. If you don't want to have this n dE dt, then you can actually translate it over to be a dE dB n over kt squared, because this will end up giving you actually if you take 1 over t, then it's going to end up, the dB dt is going to end up giving you the t squared term there. Okay. All that is to say, this is just math that you spell out by spelling out what beta is. Now you have an issue, the d beta. The reason why you want to do that is we have energy in terms of beta already. We have this. So we want to take this, we want to calculate what the du over v equals vu prime uv prime divided by v squared. The primes are the derivatives. If you follow this through, you should be able to chart each of these down. This is the derivative of u. This is the derivative of v. And then you divide it by v squared. Here's v right here. So this is, yeah, and actually the one thing about this is, let's see, we're taking the dE dB. Yes, we're doing this because we have things already in terms of beta. And I keep saying b, these Greek letters. The main thing is, this really is just a derivative, and it's a lot of e to the minus x math. You end up getting this, and this is an expression for the CV. So you actually take this, you plug it into here, so you don't forget the CV requires having this term out there, because the CV, you got rid of the dt to get it dB. Anyways, all that is to say, once you plug this into here, you get this. This is the equation you want to write down, okay? This is the CV equals n, number of molecules, total, times this lowest energy, the height of this one energy level, over kt squared times this e to the beta thing. So it looks the same, but if you calculate this out, this will give you the heat capacity of this two-state system. By the way, the other thing about the two-state system that we showed you before, the one that I showed you before, actually had a degeneracy of 4 on the upper level. So just remember, that's actually technically a little more complex. We just have two levels, one state each. If you have the 4 will be multiplied through, but it's actually just multiplied through wherever it shows up for the second energy level. All that is to say, even Dill will give you problems that are actually simpler than the 4-state, 1-state problem that we started with. We just care about the energy levels. Oh, there's my handkerchief. The thing about this, if you look at this, and you probably can't imagine what this is, but if you plug it into your computer, and you plug it in, you get a plot of CV versus T. Notice there are no numbers on this. This is just the shape of the plot. But it means if you just have two states like this, you end up with a plot that looks like this. And I don't know if you remember, but way back when, we had CV versus T. And it was actually from Atkins. It wasn't from Dill. It looked like this. For a simple system, like this one where there's only two states, you basically get this equation for CV, which just depends on the energy levels, and it just matters what, it'll just put what numbers are on the scale. This looks a little complex, but it's really just this curve. And the other thing, what happens as t approaches infinity? What happens, or actually this is B, I'm sorry, we already talked about that one. There's a peak for the heat capacity as a function of temperature, which will be where the derivative of this is 0. Just remember, you can always find a peak by saying where is the derivative 0. I don't think you're even asked to do that much in the homework. This is the kind of thing where we have to keep it super simple so that I understand it and that you understand it, okay? But that is a complete description of what's going on. Yeah, this equation gives you this curve, and this is what a simple heat capacity looks like. Okay, so how do we get S and F? We follow the same ideas. Remember that we had S equals U over T plus KB natural log of Q. There's our Q. There's our U over T. Our U is actually a ratio of the two Q's. There's Q in our U as well. That's why it gets a little bit confusing, but U equals the upper thing over Q. So we have our Q showing up from our U. We have our Q showing up from the plain old Q. And that actually is going to be S over N, is what this equation is going to end up being. So that's actually how we get that. This is actually a complete description of the entropy. And you can, this is a little more complex. I don't think most people can do this in their head. I can't. But I can plug it into a calculator and I can see what it does as it goes to infinity, as T goes to infinity and as T goes to 0. So if we have S and we have U, we have F is going to be U minus TS. So we're actually going to plug in the U minus TS, and it actually turns out, this is another thing that Dill does. He sort of gives you the end result. But F over NKT equals negative natural log of Q, and there's our Q again. See? So this equation, actually he likes to keep the things, all the thermodynamic parameters on one side and all the Q on the other side if you can. Yeah. But just notice how similar these are. Once you have Q, you can get all these different things. And so this is one we can definitely look at. This is simple enough to look at. As the energy spacing becomes infinity, remember we have two levels, and we're asking how many are at the upper level. As this gets bigger and bigger, and as it goes up to the stratosphere, eventually the excited state becomes inaccessible. 100% of your molecules down here, because none of them can reach up to the infinite energy level up there. If you look at this as EO goes to infinity, S approaches 0, and F approaches 0. So the energy and the entropy approach 0 as you have an infinite energy spacing. Infinite energy spacing is, by definition, inaccessible. If you get smaller, what happens, this is a little more interesting, because this means that these terms go down to 1. So you end up with 1 here, k natural log of 1. And this actually ends up being, as EO gets smaller, then this is actually going to be closer to, S is actually going to approach, you can move the N over, by the way. This term dominates, and you're going to end up with NK natural log of 1 plus 1. So that's the really important thing. The e to the negative x, these e to the negative x values, as they go to infinity, the thing itself will go to, this one will go to 0, but as they go to 0, they'll go to 1. And that's why you end up with nk natural log of 2. 1 plus 1 equals 2. We have that advanced math going on right now, okay? It's kind of funny, you go through all this and then you end up, your last step is literally 1 plus 1 equals 2. But that's what you're doing. For f, it's the same thing. F approaches nkt natural log of 2. Both s and f, as you get smaller and smaller spacings, that means you get more and more even distributions of particles, so that at any temperature, they will be evenly distributed because it's so small. Okay. By the way, make a note. 18C, there's a note at the very bottom that says what you should use F equals nkt natural log of 2. The question is, how are you going to calculate the Q? You always start out with that. Okay, so that's the important thing right there. And by the way, I also do this because I have a slight typo. I have natural log of EQ over N, and that should be just Q, not EQ. Okay, natural log of Q over N rather. So that's why I'm pointing you to this. There's natural log of Q. Okay. This is what I should really start off by showing you, because I want to give you the exact numbers for what you do. Okay. So you can have a temperature, you have a volume. Volume is where you move within, so you're translating, you're talking about the translational energies. The translational partition function is going to be the Q translation equals 2 pi mkt over h squared. I'm not showing you how to derive this. That's one of the things I cut from today because life's hard enough. It's kind of cool, but yeah, this is the way that we do translational partition functions. We're literally adding up that continuum of possible states for it. Basically for you, you can plug and chug, okay? So what you do, you take the mass of argon and the mass per atom. Notice that it's not per mole, it's per atom. How many kilograms per atom? Then the kT is going to be you want to use the joules per Kelvin form of K times 273, which is the assigned temperature. That equals joules. Remember that kT is actually going to be energy units. So this is a very small number and another very small number. So as long as you can handle the exponents, though, what you do is you plug them in. I guess the main thing here is to make sure you're using kilograms per atom. Then you plug them into this equation. The volume, you have it in meters cubed. So that's the other thing. And then you're going to say, let's see. Yeah, you don't use the pressure. They're just telling you this is sort of the standard volume, the volume of a mole at a standard pressure. And notice that you don't care how many are in a mole once you divide it out. You actually divide it out to each, you're calculating per atom. So that's why you have the very small number of kilograms. But you end up with this 4.79 times 10 to the 30 states per atom. So basically, if you have a sort of normalish volume, the translation that a single argon atom can be moving through that volume 4.79 times 10 to the 30 ways, different possible energy states for that argon to fill. Depending on the temperature, those states will be filled up according to the e to the minus x function. Okay? So note this: when you have a translational problem, you have, and by the way, I believe that problem 18 is this for a protein. So you're calculating with the mass of the protein. need the diameter of the protein and the diameter of the volume it's in. Because we're actually talking about the protein is taking up a significant fraction of the volume it's in, so you have to subtract the protein volume from the total volume. I say all this, and that's the last problem. This is how it ends. So once you get to this, you're done. That's the nice thing. Okay? We did that for translation. There's also the question of how do you do it for the other kinds of motion. And remember that the rotation and vibration are the ones we're going to deal with. Electronic, you know you can do an isolated problem for that, but electronic states are so widely spaced, they don't get populated in the same way. But if we're talking about what states are populated in a sample of gas at the room temperature, it's not normally, room temperature isn't enough to knock off electrons. It's not enough to ionize that gas. So we only have to worry about the accessible energy levels, which are translation, which we just dealt with, and then rotation. And rotation, though, we have to think about, rotation's meaningless for argon, right? We can't tell if it's rotating. But we can tell if H2 is rotating. That's when we get these equations. These are really physics. It's great. So the energy levels, and this is the energy levels, we actually had an allusion to this at the end of the last lecture. How something rotates actually goes up by these energy levels, L plus 1, and H bar is the Planck constant version that has the bar. Just make sure you're looking at the right one. Divided by 2I. I is the moment of inertia, and it's given by the distance r times mu, which is m1, m2 over m1 plus m2. This is actually really physics. This is what the physics of how do you rotate things, just applied to a very small level. So this is kind of all over the place, but I want you to see it's actually all here. And the Q for rotation is the summation over all the rotational energy levels. Here they are. You see this is plugged in here. And then you have this plugged in here. Remember we have the degeneracy. Because there are degenerate rotational levels. If you're rotating left versus rotating right, there's two ways to rotate, but they have the exact same energy. And so that's why you get these equations. You plug this in front of the E for G. But this is really, this is here, this is there. And if you look at this, you need to know the I to get the energy. You get that from the radius and the two masses put together. Like I said, it's actually all right here. You could do this without knowing anything about what you're doing. But I hope you'll be able to think about what you're doing as you do this. This is just the physical rotational levels that you can have for something rotating. Yeah, it's physics. It's great. So, if you have, you want to compare the rotational energy level spacing with KT, KBT. This is related to beta. Remember, this is joules, and this is a measure of how much ambient energy you have. How much will this energy be spread out? How much energy do the molecules have to jump up in energy to higher levels? So as a characteristic temperature, this is the one to write down. Okay, so this is, make sure you write this down. There's a temperature called the rotational temperature. And it is equal to h bar squared over 2I kb. Once you have that, it actually makes it simpler to write this, because then you just have a function of L and T. And this is the thing that changes from molecule to molecule. So each diatomic molecule is going to have its own theta. Theta substitutes in to make the calculation a little easier, possible to do on homework. Okay, so now that you've got that, you can see it in action here. This is Dill, rotational partition function of O2. So the length of the bond is in angstroms. You have to convert that to meters. So unit conversions never go away. So angstroms converted to meters. Grams per mole converted to kilograms per mole. And the moment of inertia per molecule, you have to divide it by molecules per mole, because it's per molecule, not per mole. Don't be surprised if you get a really small number. In fact, if you're doing per molecule calculations, be surprised if it's a big number. Something's probably wrong. You're just following this equation. Oh, and by the way, notice that the mu here is easy because mass 1 equals mass 2. That's why it's just, they just go straight from mu to m over 2. I know you have some problems that will use this. This is what you want to go to. This is how to calculate I, and then you can do other calculations based on I. Once you have I, you can pretty easily calculate this temperature, the rotational temperature. And I want you to think about how that compares with the KBT. Oh, I'm going to go back one more just because I want to see, where's our KBT? Where's our KT? It's back here. We had KT somewhere. I just want to get you to get a feel for what the KT is. I forgot where it was. Darn it, does anybody remember where we had the KT? Anyways, you can just do it by calculating it in your calculator. There was just one point where we actually had the number. And I want to show you what it is because they had a temperature and then they had the number. Oh, here it is. Here it is. Remember the KT for 273 is going to be, room temperature's KT is always going to be this. This is a measure of the energy at this temperature. The energy per molecule in a sense. So you'll be seeing that KT. It's why beta is important because 1 over KT is important. Okay. So now looking at this is how you can calculate. So for H2, you can basically calculate this up. The moment of inertia can be calculated, and you can find out for H2 it's equal to 87.5. For O2 it's 2.1 K, 87. And these are kelvins because these are temperatures. Just like we brought KT as an energy, theta is actually a temperature. For very low temperatures, you can actually do this kind of approximation. I don't think you're going to use that. There is a homework solution to using this exactly for this case. In fact, I have a slide about that, so I should probably show you that. But basically, if you are at high temperatures, when you're well above the rotational value, you can actually approximate what this is without actually having to add it up. You can approximate this adding up as an integral because you're so far above that all the energy levels look continuous. Basically, you see how this is the same thing. It's just an integral. And then you can do the integral out to get 2I kBT over h bar 2. Let's compare this. H bar over 2I kb. These are similar. So this is the Q rotational, and this is why we use theta, because it's related to Q at a very deep level. So we're H2 and N2, the two atoms are identical, and there's actually a factor of 2 that you have to include in here, that you end up putting in. I think that that's expressed by the sigma, but you aren't going to be getting too many more complex things, so that you'll be getting identical atoms, and so just use the proper equation for it. Again, this is where I'm going to let the homework show you this. It's just if you see a 2 showing up in the homework where you don't expect it to, it's like with the light. In this case, if you have 2 identical atoms, there are certain rotational states that you can't tell apart. Because of that, it actually affects the equations. Okay. This is the main thing. This is the Q rotation that you can write. And so let's see how to do it. Here's we got down to the I. And once you get the I, you plug it into here and you do the rotational temperature. And is there anything tricky to this? Take a look at this and tell me. No, that's just I. That's just K. That's just H. Just make sure that you're using kilograms properly. You're using joules and not kilojoules. They'll cancel out to be 2.08. And this is actually Dill. Let's make sure. Yeah, he rounds it off, you know, but you have different books saying the same thing. That's nice. And this sigma is the value that's related to whether it's homodimeric or heterodimeric. And so it's 2, you actually have the 2 because you have that for homonuclear if they're both the same. That's where it shows up. The 2 shows up here for symmetric molecules. So the partition function for rotation is actually going to be 300k over 2 times 2.08. This is it right here. The 2's actually cancel out, and you end up with this being calculated out. I think they did some reduction in the math to save themselves some steps to cancel stuff out. But the Q rotation equals 72. That means that 72 states, therefore many rotational states are populated at room temperature. If you are, the partition function is just 72. I want to get from here to here. I feel like there's something I need to explain about that, but I promised you I would not work too much on concepts. So I think this is related to this. At high temperatures when T is much greater than theta, because you're doing an integral and stuff like that. Okay, so this is the homework problem you're going to use it for. And there actually is an answer in the back of the book, but there's a better answer that's been activated on Canvas for you to look at from this, okay? So you use it's really go through and use these equations. Here's Dill's book. It goes through and it will actually calculate these different things, slightly different units, but you're going to end up with the temperature for rotation for each of these, and you see that for like O2, the temperature for rotation is really low. And the higher this is, actually the easier it is to rotate. I believe I2 is harder to rotate, and so the rotation temperature is actually lower as a result. Okay. Notice there's also a theta vibration and even a theta electronic. Like I said, see how big these are? These are not going to be affecting our normal gas phase kind of calculations. What matters is when your temperature is well above that, that's when you're getting so much that you can do things like integral calculations. Okay? As long as we are not above 11,000 Kelvin, we don't have to worry about electronic transitions working. But we do have to worry about vibrational stuff happening when we are actually around iodine and things like that. We can get some vibration happening. Oh, and the other thing is right here, this is actually what I want to point out. This is the degeneracy of the states. There's actually some interesting degeneracy that goes along when you have O2 and NO. I believe this is because of their weird paramagnetism, and it has like lone pairs and stuff like that. So that's just something, but yeah, I don't think that Prigogine even cares about that. Oh, and the other thing is, notice you actually can tell what gets a 2 and what gets a 1 for sigma. If you have two different things, it gets a 1. If you have two the same thing, it gets a 2. Okay, so we've got one more to do, vibration, and then we've got a little bit of concepts after that. But vibration is actually similar to before. It's just that you have this, which is actually, isn't this related to the equation for a spring? Because when we're talking about vibration, we're talking about a spring vibrating. I think you can actually get this equation. I'm not sure, this doesn't ring a bell from physics when you talk about springs. Did you talk about the vibration of a spring? Possibly not. Chemists care a lot more than physicists about spring vibrations, because it's a really good model of what goes on with a bond. Anyways, this is the equation. This is how you get the energy level for a vibrating spring, and it's quantized, so it can go up from 0, and the levels are always equally spaced. For the same bond, you can vibrate it, and you can quantize it up, but they are going to be vibrating it twice as fast, gives you twice as high an energy level, and it's actually quantized, and they're equally spaced and non-degenerate. That means you will never have a G to throw in. There will always be a degeneracy of 1. That actually makes the calculation easier, because the definition of the partition function is the sum of all the vibrations, and it's going to be, basically it's this, you take this equation, you do the sum of it, And you can move all this stuff out, and you just end up with x raised to the frequency when x is beta, h, and omega. What is omega? Oh, it's the proportionality constant. Okay? This is actually spring physics, but we apply it to atomic bonds, and it works. X is much less than 1. If you look at the reasonable values for this, x is going to be much less than 1, and so you can actually take this and use that as a math trick to sum this up as 1 over 1 minus x. So you don't have to do this at all. That means that you would just have the vibration is going to be 1 minus x, and our x was defined up here, and there we have it. That is the vibrational partition function. I believe that's a good one to write down. All of these start with finding Q. Remember, once you have Q, you actually have most of the problem done. It's just a matter of calculating and canceling. And it's a reason why I give you open note tests. I don't want you memorizing this. And by the way, the ACS does not expect you to memorize this. But it will ask questions about what Q is in general. And if you do this enough, you're going to get a feel for what Q is and what degeneracy is. And we will talk about that more on Friday. So by the way, I know that homework isn't due until the test, but it would be really helpful for you to work through some of these before Friday, before math day. So we could jump right in. And what I'm going to do is I'm going to focus on the ACS. So, at ordinary temperatures, the level spacing, remember vibrational is bigger than rotational, which is itself bigger than translational. So generally, and you notice that our temperatures were really high for that column. Look at them. These are high Kelvin temperatures. So the thing that applies to rotation, molecules are always rotating. They're not always vibrating. And in fact, can you find a triple bond or a double bond rotation? Single bond, N. So its rotation, its vibration is, let's find something, N, let's compare N to O2. That's a pretty big difference. I think the triple bond versus a double bond affects how it acts as a spring, but I'm not really sure. But you can actually dive into these and have some ideas like that. But the main thing I want to show you, when you're well above this temperature, then you can integrate. You can't integrate here, but that means you can count. You can count how many are in. You can do a sum instead of an integration. Okay, so because of that, so we're going to define vibrational temperature. This is going to be h bar omega divided by kb. Here we have omega. Well, here we have them. I went back to that. Here I had the numbers right here. Right? Okay, anyways. But basically, what you do is you can plug in this vibrational temperature for each of these. You can use this to calculate the partition function relative to temperature. And if you have T in the range 200 to 400, only a few states are well below this temperature, which means, and roughly the temperature of each of these things, the vibrational or rotational temperature, is kind of the temperature where the lines blur together, where they go from being discrete to looking continuous, where you can do an integral rather than a sum. And again, we're well below the temperature, so that means only a few of the states are occupied. And so electronic states are even higher, so most electronic states are, most atoms floating around right now are in the lowest ionization state. Not many atoms ionize by themselves, just for the fun of it. Temperature does not cause it, I should say. You can cause it by another reaction, maybe, but that's not temperature. We care about temperature here. These concepts will answer you a lot of good questions on the ACS test. Okay, so here's Dill's example. He's doing O2 vibration. And let me just double check that the equations look the same. Yeah, he does it in a slightly different way. He's doing H frequency over 2 kT.
And that's what I want you to do. I'm giving you homework problems from both of them, but Dill probably is the one to start with. Again, I trust him more when it comes to teaching this stuff. This is his wheelhouse. Okay, so oxygen molecules, they have a vibrational frequency of 1580 per centimeter. And you need to convert that to units of per second. So how do you do that? Meters per second. It's light, and so it has the speed of light, and you get per second. So now you can calculate the vibrational temperature. Plug, plug, plug. And you end up with 2274, which hopefully coincides, yeah. Basically, this just comes from using different values for this original thing. It's the same calculation, just different source values. So at room temperature, if you take the ratio of the two, at room temperature, this is a small ratio. So for the partition function at room temperature, if you take this and plug it in, equation 11.26, and this is why I brought the book. I want to look up equation 11.26 because it is how you go from partition function to fraction. So it's 11.26, right? Yeah. Oh, that's what it is. I have it up there. This is equation 11.26. I thought of everything. I just don't remember. If you plug 7.58 into this, well, it's not that straightforward to plug into. You have to go back and you have to plug some of these things in. If you plug and chug these values into this equation, you end up with 1.0005. That means that most oxygen molecules are in their ground state, and like 0.05% of them are not in the ground state. I think that's at least a rough calculation. Even at 1000 K, you end up with 2.27. This ratio goes up to 2.27. And then you end up with a whole grand, like 11% of the molecules start to be in their upper vibration state. It takes a lot of energy to vibrate, not as much to rotate, and definitely not as much to translate because atoms are moving like crazy all over the place. So just remember, when you see what fraction are going on, you think of this equation, and you want to do the Q vibration gives you an idea of the ratio. Technically, it's 1 over the fraction. You have to think about it. Remember, it's the total that are going to be, but if it's close to 1, you can think of it roughly as being, most molecules are in the 1, and then you have 1 out of 20,000 or whatever. You can actually do that calculation. Just remember, this is technically a summing up of all the states that the atom is accessing. They're in the upper states by an e to the minus x function. It's just a very flat e to the minus x function, okay? I want to tie it back to that. Okay. So the great thing about partition functions, we went through all this because that you can just add them up. Partition functions are probabilities, and they will actually multiply instead of their equivalent of adding. Remember, there's natural logs in there, and that allows us to multiply them together. So you end up with this mess, right? But each of these is the Q for that particular thing. There's the Q for translation, the Q for rotation is in there, and the Q for vibration is out here. And the big Q, if you're talking about the big Q, this is the way to calculate actually the fraction that we were talking about. Because this is like the 1.05 right here, this is the 1.005. And so if you have the 1.005 here, you can figure out how many molecules are in the higher state by using that, okay? I guess that's one little thing that was at the beginning, so I want to point that out, okay? This Q vibration goes in here in this equation. If you have 10,000 molecules, you can calculate how many molecules are in the ground state and in the other states by inference, okay? By subtracting them from the total. You choose your n. This is, and remember, this is why I showed you the average math at the beginning. When you're taking an average, you divide it by the total. This just means total. So it's really, the first time you do it, it's tricky. But again, that's why I'm giving you the answers in many cases. And then once you do it, you can go back and you can calculate this. By the way, remember, I just realized, this is how you go from the partition function, the little q, to the number of molecules in the level. And I was just doing it approximately in my head, but you can do it for any number of molecules. Pick a number of molecules that makes the calculation easy, you know? So, okay. So you can also calculate, so if you can calculate Q's for everything, you can calculate energies, you can calculate anything. All of these things are energies that add up. If they are probabilities that multiply, they're energies that add up. Everything is great. You can actually go through and you can do like heat capacity. You can even do full calculations. So sometimes the problem will look pretty simple, but it will be saying, you'll see that you'll need to calculate all three of these and then add them together. Like the heat capacity includes contributions from this plus that. But you just divide and conquer. Take each U separately, solve it, add them all together when you're done. And you can see how the different motions contribute to the heat capacity, which is actually, you can actually take that and you can figure out a lot of things about how the molecules work. Okay. So now we've got heat capacity we can measure in the lab, and we've got statistical thermodynamics that calculates what the heat capacity should be. They should match. Let's hope they match. Well, they actually do. So here's an example. You can measure entropy. So what's the absolute entropy of argon? So we're going to take this equation. By the way, he gives it a name, the Sacher-Tetrode equation, which is kind of cool because it involves S. But you don't really have to remember that. It's just, notice it's how Dill labels it. You've seen this before. This is the S for translation. And we're talking about argon, so no rotation, definitely no vibration. There's no bonds. It's just a sphere. We just have translation. So the entropy is given by this. We want to calculate it at 300 and compare it to experiment. So actually calculate it in example 11.2. Did I give you 11.2? I think I did. Oh, it's all the way back here. 11.4. There you go. So we calculated how many states per atom there are. We calculated but this was at 273. Well, the good news is you can actually use that to go forward. It's just a ratio, so the Q translation has just changed by T is changing this value, so it actually changes the ratio. You can actually just do the ratio as long as you treat it properly. The Q translation at 300, and actually this is going to something that I cut at one point. I think I cut exactly what they're doing here. So I'm not going to ask you to do exactly this. But the idea that you can do a ratio, the question if you wonder where 3/2 is coming from, it's actually coming from something that I'm glossing over this year. It's coming from this right here, this kind of thing. But this is where I'm, or something like that. Anyways, whatever it is, I don't want to spend too much time on it because I'm not going to make you do it. But the main thing is if you've already calculated one temperature, it's actually just you figure out mathematically what's going to happen when I change the temperature. And he calculates that out. You end up with 2.47 times 10 to the 32 times the volume that you have there. And you can substitute this in to get an expression for S over N. This is the expression that was shown earlier. And you plug this in, you will get this expression for, you have, he's keeping V over N. You notice you aren't given everything that you need for this. He's just calculating what the different things are. And then what you want to do is you can use V over N equals KT over P to go through to this and to calculate S over N. I think that's a weird way to do it, honestly, because we have another equation that we can just plug and go to. So he's trying to tie things together, but the main thing is you go through this, you get the S over N from the calculation, and you actually got 154.8. You actually measure the entropy of argon, you get 155. What do you trust more? You actually trust this. because the instrument is going to have error in it. There's more error in the instrument than in the calculation. Because typical sizes of errors, now you hope that you can get the error down, but for thermodynamics, there are some certain errors that are probably built in. Anyways, I would be happy if I got that from the lab report, calculated 154.8 and I got 155, and so we can be happy with it. And basically doing the same thing and applying it to monatomic gases, then you apply it to diatomic gases, accounting for rotation and vibration. You can add them all up. It's a lot of work, but physical chemists have already done it. And so you have the calculation here, and you have the calorimetric. This is what we just did. And you notice how the calorimetric is really, really close to the calculation. So we're actually trusting both sides of this. Okay. This is the main thing that you want to put all this together. We've given you a bunch of equations. What you do is you look at the equation and you go. It's actually not that different from a usual kind of problem. You look up the equation and you go through it. There's actually not that much hidden or hard to find once you've found the equation. But the main thing that you want to notice is translation is always easiest. Electronics is always hardest, and it's so hard that you don't even talk about it sometimes. Vibration is next hardest, and then rotation is second place. Okay? And so if you think about this, there's an interesting kind of factor to this. You actually have from these equations, notice that you have this 5 halves flowing through, you have the 3 halves flowing through here. The translation has a 3 halves thing. Then there's other levels that have a 5 halves. This is the actual numbers. I'm glossing over why those numbers are here. But I want you to notice, I want you to have this in your head. Relative to the rotational, vibrational, and electronic temperatures, at each temperature, you kind of fill up that mode of motion. This is a graph that I actually want you to know. This is, and this kind of sums up a lot of things. When you're at translation only, when you're really cold, only translational energy levels are available. When you get close to the rotational temperature, then by the time you reach the rotational temperature, you start to fill up, you're really filling up the rotational levels. This is always, at a CV over R, is always going to be 3 halves. This will fall out of the equations. And again, I could take the time to prove it to you, but again, I'll leave that if you wonder about that. If you take these equations, they have a lot of the same terms in them. They all have Q in them, right? It turns out if you take translation only, and CV over R, you calculate CV over R, you actually get 3 halves. When you increase T to be close to the rotational, then you fill up the rotational, and you end up at a CV over R of 5 halves. This is true for any simple molecule. Probably not true for proteins, so that's because there are other things going on. It's true for chemicals. All the chemicals in that table. And so look what happens. You get the extra CV from the motion of the molecules in a new way. Here the molecules are so cold they can only move, they can only translate. When you get them this warm, they start to rotate. And your heat capacity, which is how the energy can go into motion, opens up a new way for them to hold heat. And it's always 5 halves. If you have things in units, in the proper units, you can actually say it's always 5 halves. When you get it up to the T vibration, you fill up the vibrational levels and its CV goes up again by the same relative unit. This is related to the thing that we talked about in the previous lecture. Was it the previous lecture? Yes, it was, because we had Monday off, Friday's lecture. Where we talked about how the CV always approaches 3 on one scale. This is the same exact idea. When you're changing the temperature, the CV actually has a constant number, and you find this commonality for all matter. So, what you can think of it as, if you're too cold for a particular motion to happen, that motion can't hold any heat. You can't put any joules into the system, and it can't be holding them in the motion. This is how you can think about heat capacity. You can actually think it through this way. So if you have really hot temperatures, you can cool them down, then the heat capacity is going to be around 7/2. You cool them down more, and it's going to be around 5/2, because you are not going to be having much vibration anymore. When you get below the vibrational temperature, you start to lose the vibrational states. You lose the vibrational contribution to the heat capacity. And so if there's something that ties together this whole class from beginning to end, we started off with saying heat capacity is how much you put energy into a system and its temperature changes. We had it as being a completely, measurement-based thing. Well, it turns out that when you are, you can actually relate it to motions. So it's a simple temperature because the energy is distributing to the newly available type of motion. And there's one important thing, and I think I can tell you this is on the ACS in some way, okay? When you move through these, you have a degree of freedom. You literally have a new kind of motion that you can do when you get to that temperature, and you start to fill up those spaces. And so they call each of these a degree of freedom: translational, rotational, and vibrational. Technically, translational is a little bit weird because the other ones you have only one axis or dimension. Translational has 3 dimensions. It's part of the reason why it's 3 halves rather than being 2 halves like you see the other ones. But you can even think about that. Okay, this is, I believe, I want to make sure that I'm not forgetting something. Yes, this is it, and then there's one more thing. Okay. The equipartition theorem says that you're going to uniformly distribute the energies to each degree of freedom that is available. In other words, if the degree of freedom becomes available, you distribute everything equally and fairly across each degree of freedom. There's no unfairness. The only unfairness is whether you have enough temperature to even access that. Once you access it, you can spread out among the whole degree of freedom. It becomes available to you. And I want you to get that conceptual. I am not going to cover it this way, okay? So, but that's the thing about it. This is cooling a hot gas leads to the freezing out of degrees of freedom. This is the concept I want you. As you get it cold, you don't have the freedom to lose electrons. And your heat capacity actually goes down because it cannot go into losing electrons. Here's experimental data, and you can actually go below the theta. Remember, at the theta, you actually are accessing a ton of the vibrations. But as you get right below it, you get colder and colder. And if you calculate out how temperature relates to CV, and notice this, 3.5 to 2.5, exact same number. We're zooming in on this right here. Basically, you measure the CV, you get this at the proper temperature. One more thing, and this is something that you'll mostly work out. I'm not going to go into too much detail here except to show you. We talked about all these things. We haven't talked about how the D of potential equals dF over dN. I'm not going to show you all of this except to say we're talking about energy levels. And we're talking about going from X to Y. It's a pretty simple equation. What matters most is the lowest energy level to the lowest energy level. But remember, you have an e to the negative x distribution among each of these different populations of molecules. So we've talked about each of these individually, and now we can talk about how you move from one to the other. How you move from one to the other is the dF/dN, which is the chemical potential. If we have an expression for dF, we can actually calculate d potential. And so it's actually not that hard. That's why I squished it all on here. But I just want to show you, it's just complicated because you have to have so many terms from having all these things. So I don't want you to worry too much about this, except you can reconstruct the algebra if you want. But the main thing is right here. You calculate how the F changes. You have an expression for how F changes with Q, so you can plug in Q there. And just
go back to this kind of equation if you're calculating chemical potential, but I think you're taking it one more step. You can calculate potentials, you can calculate Ks. And so this is the one for the chemical potential, and let me flip this over. The reason why I'm not going that much into this is because I want you to go through Dill's example, apply it to the problem. Or did I take away the problem? I hope I did. I might have taken away the problem when you do this. So, but just in, bless you. Yeah. Oh no, there's an MT problem. That's why I did it. At the very top, I made a note to myself. The MT homework 20.6. You don't have an answer for that. But it's about the equilibrium constant of H2. What Dill gives you is the equilibrium constant of HD, which is actually more complex than H2. Like if HD is heterodiatomic as opposed to the homodiatomic. So this is close to an answer for 20.6. And that's what I will leave you with. And it's exactly, oh, it's like you 1 minute over. Okay, so like put that on all your class evaluations. I go far over. But needless to say, remember this is what people, gives people problems, but I have set this up so that you have your notes, you have the ability to work on it, and to look at the examples. Always start from the examples. And that should actually make it clear, because Dill is very good at telling you what he's doing. And that's physical chemistry. Okay? Friday we will meet in here. I actually want to spend most of the time talking about the test and the ACS test, and I want to talk about how they're going to do it. Like I said though, try to work on this. If you do get stuck on one of the ones you don't have an answer for, we can try to work on that as well. Or I can do that over email if you find out later. But I want you to please do something before Friday, so that when we're doing this, we can have the concepts, and then we'll talk about the concepts rather than the equations. Okay? All right, thank you for your attention. We've got one more class between us, and then, and of course we have the presentations on Tuesday night as well. Not for you to see, but for you to listen. All right, but I'll see you Friday.